So title of my talk is Trisections of 4 manifold, which is a decomposition of 4 manifold recently introduced by Gay and Kirby. So these are my outlines. I will just first introduce the notion of trisection of 4 manifolds and some significance of trisections. Then we talk about some results on some of my recent results on trisection embeddings and Moravsky sum of trisections of 4 manifolds. So Gay and Kirby recently introduced the notion of trisection of closed orientable 4 manifold and the notion of related trisection of combined orientable 4 manifold with connected boundary. They also proved the existence of closed orientable trisections of closed orientable 4 manifold and existence of related trisections for combined orientable 4 manifolds with connected boundary. Further, Castro and Gay and Castro studied related trisections of combined orientable 4 manifold with multiple boundary components. So this notion of trisection is analogous to the notion of the Higard splitting of 4 manifolds. Let us regard the notion of Higard splitting. A genus G Higard splitting of a compact orientable 4 manifold M is a decomposition of M into two genus G handle bodies Hg and Hg prime. Here the genus this is the genus B handle body Hg and Hg prime, and they have a common boundary sigma G, which is nothing but the boundary of Hg and boundary of Hg prime. So this M can be reconstructed from the handle bodies Hg and Hg prime by gluing along the boundary using an orientation reversing diffeomorphism F which is on the boundary map, which is a boundary map. So if you see the handle body Hg, those has the curves, these blue curves, which are bounding discs in the handle body Hg. So one can cut the disc if you cut the disc bounded by this blue curves, whatever you are getting is disc D3. So this handle body can be decomposed as union of discs G discs and some union of two discs G2 discs and one disc D3. Now, if instead of attaching H2 to Hg prime along the boundary, let me just attach these discs along the image of this curves first. Then I will attach the disc along this D3. So we will get the same manifold M. But by Alexander trick, one can see that this attaching the disc D3 to the resulting manifold will not matter actually. Like it will be like giving the unique manifold. So this manifold M can be obtained by uniquely by this attachment, but this attachment only determined on the map on these curves, these blue curves. So this Higard splitting can be encoded by two things which are like cut systems alpha and beta and sigma, such that they bound G disjoint discs in Hg and Hg prime. Here these blue curves are representing this alpha curves, one cut system in Hg, and these red curves are representing another cut system of Hg prime. So these blue curves here represents the image of this blue curves under the map F. So this data can be together form something notion called Higard diagram, which is sigma alpha beta, which uniquely determine the Higard splitting of the manifold M. So here is the Higard diagram of this guy. So now we define the notion of trisection. So as I said, this is generalization of Higard splitting. We will see why. So a GK trisection of a closed orientable 4 manifold X, a decomposition X into 3 pieces X1, X2, X3. Each piece Xi is diffeomorphic to bounding and reservoir cos D3 called sector, which is a 4-dimensional one handle body, and the double intersection is diffeomorphic to bounding and reservoir cos D2, which is the 3-dimensional handle body, which we have seen already in the Higard splitting, which is called spoke, and the triple intersection is a closed orientable surface, which is called core. And the genus is called the genus G is called the genus of the trisection. So here is the schematic of the trisection of the manifold X. These are X, and these are the double intersections which are drawn in color. And this alpha, beta, gamma represents the curve system corresponding to the cut system corresponding to the handle body Hijs. So here this alpha, beta, gamma is encoded in sigma G. Like in Higard splitting, we have two cuts, sigma and then two cut system. Here we have three cut system alpha, beta, gamma. That we will see later. So these are some example. I have drawn in for Sn instead of S4 because actually this definition can be generalized to Sn also. For example, here in this definition, Xi can be taken to be bounding conditions of S1 cross Dn minus 1. and intersection to be boundary condition of G compass of S1 cross Dn minus 2, and triple intersection to be closed n minus 2 surface. I mean, closed n minus 2 manifold actually. Like, so these are handle bodies. Like basically these are decomposition into handle bodies. So this is a skip. This is a decomposition of Sn, which is obtained by the trisection of this disk. We are just pull backing the trisection of disk to the sphere. Like here, the sphere is embedded in Rn plus 1. This Rn plus 1 can be thought of as Rn cross Rn minus 1. This is the unit sphere in Rn plus 1. So now we put the trisection structure on this R2 and pull back the trisection to this Sn to get this decomposition. So one can easily see when we have the last trisection in Sn, if you just take cross S1 to each pieces, whatever we are getting is some trisection of S2 cross Sn cross Sn, S1. So this also one can define generally. So I have driven. So similar thing can be defined for manifold with boundary also. Here this is, I have drawn this for Dn. I have not defined the notion of related trisection, but this is also similar notion, which are like nice intersection with the handle, like this connect some of boundary connects of S1 cross D3s. So here this also same, this is also coming from the same example. We have disk in the D2 and then we are embedding this Dn into Rn, and we are just pull backing the trisection structure of disk D2 into Dn. Okay, as I said, as in Higard trisection, Higard splitting, we have Higard diagram. Here actually we have trisection diagram for the trisections, which is a 4 tuple sigma, alpha, beta, gamma. Sigma is a closed surface, which is the core of the trisection, and alpha, beta, gamma are the systems on alpha, beta, gamma, which are corresponding to the handle body HIJs. So these are the handle body which are bounding G disjoint disks in HIJ respectively. So this trisection notion having more structure, complexity comparatively trisection, regards trisection, related trisection have more complex structure comparatively trisection due to boundary. For example, it has open book structure on the boundary of the core manifold. So these are some regard trisection diagrams of trisection of S4 and CP2, S1 cross S3 and S4. This one is an example which I was showed last slide. This is the D4 which I have shown last slide, and this is the diagram of related trisection of 4 manifolds with compact 4 manifold with boundary. This is D4s and S2 cross S2 and D1. D1 is a disk bundle over S2 with Euler number 1. So we see some significance. Known results in known invariants of 4 manifold are insufficient for smooth 4 manifold conjecture, which says that every homotopy force pair is diffeomorphic to the standard force pair. People are believing that this trisection notion can be useful to study the Poincare conjecture due to the following reason. If you prove additivity of trisection genus, then that implies the smooth Poincare conjecture due to some known theorems from 4 manifold topology. So there are other invariants already studied using trisections. For example, this Kirby and Thompson's invariant, that they introduce an invariant called L invariant, which is a closed 4 manifold, which is an integer invariant of a 4 manifold X defined by minimizing the certain complexity of trisections of X over all trisections. So also they have proved if Lx is 0 for homotopy force pair, let's say, then X is diffeomorphic to the force pair. They also proved if Lx is 0, if and only if X is diffeomorphic to connected sum of copies of S1 cross S3, S2 cross S2, CP2 or S4. So now we see some history about embedding problems due to, I'm going to discuss about trisection embedding. So we just see some history about embedding problems. So Whitney started embedding problem in 1944, and he proved that any compact n manifold embeds in R2n. People again reduce the dimension by many people have done those. Here I have mentioned some of them. So any close to oriented form n manifold embeds in R2n plus 1. They have reduced the dimension to 1 plus. So this is due to Hirsch, Haplinger and Messi Peterson. But in non-orientable case, there are some weird thing happens. So there are some obstructions basically. So we have two cases. When n is not equal to 2 power n, any close to orientable n non-orientable n manifold embeds in R2n minus 1. This is also due to Haplinger, Fierce, Messi, Peterson, and Rocklin involved. But when n equal to 2n, there is abstraction, which says that a closed orientable n manifold, closed non-orientable n manifold M embers in R2n plus 1, R2n minus 1, if and only if this Stephen-Italy class is 0. This n minus 1th mod to normal Stephen-Italy classes of this M is 0. So this is due to this guys like R2n minus 1. First is R2n. Yeah. No, 2n plus 1 is, I mean, he proved for any general n, very large n, and he proved for 2n also, like R2n also. So now we see some structure preserving embedding. Like we have seen embedding problems. Recently, people are interested in structure preserving embedding, which says that like not only embedding with some decompositions, preserving embedding. So for example, we have open book embeddings due to these following peoples, and ellipsis vibration embedding and contact manifold embeddings and all. Like these are some references for that. Like not all, like some. Now we see some of my results on trisection embeddings. So here I have proved this theorem says that every closed connected orientable 4 manifold with a given trisection, admitted trisection embedding into trivial trisection of S side. Here trivial trisection I mean which I have shown already. Like I have given the example of Sn. That's a trivial section of Sn, in particular for S side. So here trisection embedding I mean the embedding of trisection into S side, which preserves spine, spokes, and core, everything like 4 manifolds. Spine has to go to spine of 8 manifold. Like every pieces are preserved in that way. In other words, if you restrict the trisection, like if I restrict the trivial trisection of S side to the 4 manifold, embedded 4 manifold, I will get given trisection of 4 manifold. That's the embedding definition roughly. So this theorem we have proved using the Spamer's theorem of Urs, which says that any two embeddings of a closed smooth n manifold in R2n plus 1 are isotropic for n greater than or equal to 2. We also have proved related restriction embedding. As I told already, we have some more structure on related restriction. We have this result. Every related restriction of compact oriented smooth 4 manifold with an non-empty boundary. I mean, we can take many boundary components. Admits a smooth related restriction embedding into trivial related restriction of D8. So this also we have seen it. Trivial restriction of D8 only I have given the example. And trisection embedding, related restriction embedding can be defined analogous to the trisection embedding. So this is the decomposition of this related restriction, and it is the just rough figure. So here, due to complexity, we have to use some other way. So we constructed a specific proper flexible embedding of compact surface, orientable surfaces of genus G with B boundary component, like into the this D6. So here we mean flexible embedding. We mean by a flexible embedding we mean an embedding of sigma into D6, such that every diffeomorphism of sigma can be realized by an isotopy of D6. So basically, like we have this commutative diagram of the isotopy. Let's say this is the diffeomorphism, and this is an embedding, and there is an isotopy here, like. So this diagram computes. So now we recall the notion of open book decomposition. Now we define. Now we see some results on Moraskism. So we define the notion of open books. An open book of a closed oriented 3 manifold M. Say way to express M as a fiber bundle over S1 in a common element of a link B in M, such that boundaries of closure of each fiber is B. So here is the schematic of the open book diagram. So here this B is the binding, and these are the pages, like these half planes are the pages. Basically, this is the open book of R3. So these are they have common boundary B. So this open book data also can be encoded in a tuple in pair sigma comma phi, where sigma is the page of the open book, this page, and phi is the monotomy of the fibration. So here we have a fibration phi in the common element of P. So we have this monotomy and the fibration. So Gaba introduced the notion of Moraskism of open books, which is a special kind of plumbing of manifolds. So the notion of monarchism is defined as follows. Monarchism of open book sigma 1 phi 1 sigma 2 phi 2 of an open is an open book sigma 1 star sigma 2 phi 1 star phi 2, where sigma 1 star sigma 2 is obtained by plumbing sigma 1 sigma 2 and phi 1 star phi 2 is actually phi 1 tilde composite phi 2 tilde. Here plumbing we mean this diagram, like this is the local figure of sigma 1 sigma 2 and we have some we have embedded arc in arc properly embedded arc in sigma 1 and sigma 2 and thickening of that, and we identify in this manner to get sigma 1 star sigma 2, and phi tilde is defined by phi tilde is extension of phi, extension map of phi to the sigma 1 star sigma 2 by the identity map in the complement of sigma I. So we have this phi is defined on sigma I. So in the complement of this guy, this region, we make it to be identity. That's the definition of phi tilde. So Gabay also proved the manifold associated to the Moravsky sum of open book is the connected sum of associated manifolds. So basically he did like after doing Moravsky sum, if you do the construct the open book, whatever you are getting is the connected sum of manifolds. So we also have similar results. That's why I'm just motivating from that. So the notion of Moravsky sum of related restriction can be defined analogously. I'm not going to define here as for time reason. So Castro and other people gave an algorithm to plumb two related restriction diagrams of x1, x2 to produce a related restriction of x1 boundary connected sum x2 such that the induced open book on boundary of x boundary comes to x2 can be chosen to be any desired Moravsky sum of open book of boundary x1 and x2. Here that means Castro and other people has used open book Gabay's result, like open book's Gabay's result to prove this result. Like in the boundary we have open book structure, so we can use the Gabay's result to produce open book connected sum, and they extend that into the 4 manifold level. So we have a similar result. We have reproved this result using some schematic approach, but without using Gabay's result. So they have used Gabay's result on the boundary to extend the extend to the inside, but we have without using Gabay's result, we have proved this result only diagrammatic level using diagrammatically, and in fact Gabay's result to be Gabay's result is corollary to our result actually. So this is the statement of a result. The 4 manifold associated to the Moravsky sum of two related restriction diagram D1 and D2 associated to the 4 manifold Y1 and Y2 respectively is Y1 boundary connected sum Y2. So we also have similar result for closed manifolds. So this is we introduced the notion of T related restriction diagrams for closed manifolds. So this result is for compact manifold. They have proved. We have introduced some Moravsky sum notion for closed manifold, and we prove this following result. A trisection diagram associated to a Moravsky sum of two T related trisection diagram D and D prime is diffeomorphic and horizontally equivalent to connected sum of trisection diagram associated D1 D2. So this allows us to define the notion of Moravsky sum for closed 4 manifold also. Basically, this is analogous to Gabay's result. Like here proved for closed manifold, here also this we have. So this is all I have today. These are some references.